Ladies and gentlemen, welcome back. We now gather for our final technical session of the day, themed The Pulsing Planet, Orogenic Forces and Rhythmic Resonance. This session brings together compelling studies that explore how the Earth's crust moves, deforms, and evolves through time. From journeys deep towards the Earth's interior to the behavior of major shear zones, to strain patterns across the Himalayas and fresh insights into the tectonic history of Vidyan Basin. With that, let's begin with this final session as we dive into the dynamic forces that continue to shape our ever evolving planet. To guide this session, we are honored to have with us chair for the session Dr. N.V. Chalapati Rao, Director, NCESS, a globally recognized geoscientist with dual PhDs and pioneering contributions to igneous petrology, geochemistry, and geodynamics. I would also like to extend warm welcome to our co-chair, Sri Avik Manna, Superintending Geologist, PSS PNM2 GSI, who brings deep expertise in national geoscientific planning, advanced mineral exploration, and strategic mission monitoring. I please invite Dr. N.V. Chalapati Rao and Sri Avik Manna to join us on stage. Please, sir. Thank you, sir. I would also request Dr. Kevil, GSI WR Jaipur, as our reporter to record the proceedings of this session. Please come on a dais. Starting with our sessions, it is my honor to introduce Professor N.V. Chalapati Rao, Director of the National Center of Earth Science Studies, Ministry of Earth Science, Thiruvananthapuram. He joins us on a 5-year deputation from Banaras Hindu University, where he serves as professor in the Department of Geology. Professor Rao holds dual PhDs from Osmania University and University of Cambridge and completed his postdoc research at the Technical University of Clausthal, Germany. His work spans kimberlites, lamproites, carbonatites, and large igneous provinces with influential contributions in petrology, geochemistry, and geodynamics. He has published over 125 SCI papers, edited multiple volumes, supervised 18 PhD scholars, and is a fellow of INSA, IASC, NASI, and JC Bose Research Grant Fellow. His remarkable career has been recognized with numerous prestigious honors, including the National Mineral Award, the National Award for Excellence in Geoscience and Technology, the PRL Award, Krishnan Gold Medal, and several other distinguished medals. We are privileged to have him deliver today's keynote address titled A Journey Towards the Center of the Earth. Sir, please.
So good evening, everyone. It's a great privilege to be here standing in front of you delivering this talk. I would like to congratulate the great Earth Science Organization, Geological Survey of India, on completing 175th year. I recall in 2000, GSI, when it celebrated its 150th year, I was in Ministry of Mines I was a scientific officer at ore dressing division of Indian Bureau of Mines at Nagpur. Then I think S.K. Acharya was the DG at that time. There was a huge function, and now time flies like anything. 25 hours down, years down the line, we are celebrating 175th year. And second, I should also thank the organizers for inviting me here and also for accommodating my request. Actually, I was to come yesterday. I had some important commitment, so I could make it today. Though in the last minute, they agreed to reschedule my presence here. Thank you. Now, the topic I am going to share, the title, is the outcome of a very interesting research project done by one of my postdocs, Amitava Chatterjee, who is now a faculty member at University of Pondicherry. It came out during the COVID time. So I would be taking you towards the center of the earth. You all know the title is a borrowed title. It's taken from the very famous novel, perhaps one of the greatest scientific fictional novels of Jules Verne. So I need to quote him. So what I'm showing on the screen is an eclogite sample. Eclogite, you all know, for those who are not petrologists, eclogite is a very high pressure, high temperature facies metamorphic rock with omphacitic pyroxene, pyropic garnet. It may contain zadiate, kainite, and such high pressure phases. And this is a thin section of a what you call garnet bearing eclogite sample. So I would be basically taking you through vis-a-vis the eclogite sample which we encountered, and I would like to enumerate the significance of that finding in the next 15 to 20 minutes. You can change, yeah. So human being is always fascinated by two things. Human being is always fascinated by things which he or she cannot access. One is outer space and the other one is the deeper earth. And for geologists, we are always excited about things, what lies below, because we can't see, that's the first thing. And many of the products which we see, either rocks or mineral deposits they are an outcome of the processes which take place quite deep, far within the deep earth. So unless you understand how deep earth functions, we can never understand how mineral deposits form, how earth itself has formed, how life has formed. Everything has to come down to that scale. So to know what lies below the earth, the most obvious way to look through it is through geophysics, seismology. In the morning, Professor Sen has shown how important seismology is. That's the first thing. The second thing is experiments conducted at elevated temperatures and pressure, because experimental petrology has come in a very big way, all the phase diagrams and all, because we can simulate those temperatures, pressures in the lab scale, and we need to verify them by natural means. That's the second way we know what lies below the earth. And nowadays, another way by which we know is computational mineral physics. You use density function theory, and you predict what are the possible mineral phases which are present. It is coming in a very big way. In India, there is a small beginning made in the Saha Institute of Nuclear Physics. People are working on that, but that has come not yet become a big thing in India right now. And why that is important? Because your seismic velocity interpretation is based on the mineral phases present. So we simulate few things in the lab, but theoretical mineralogy, that's what it means, also plays a very important role. And of course, you all should remember that neither geophysics nor experiments conducted at elevated temperature pressures, nor density theory, function theory, what the results they give, they are not absolute. They have to be verified. For geologists, outcrop is the ultimate truth. Whatever is validated in the field is truth. But how to validate things which are in far earth? Then we depend on proxies which come from deep mantle. Rocks like kimberlites, lamproids, lamprophytes, these magmas come from depths of 150 kilometers. They are the deepest formed magmas, and while coming up, they bring a lot of natural products like xenoliths we call, including diamonds and all the materials. So they provide the proof of what's actually happening in the deep earth. Next slide, please. So if you see this cartoon, what is shown is on the x-axis, the modal percentage of common mantle minerals, and on the y-axis, you have pressure in gigapascal. 1 gigapascal corresponds to 10 kilobar pressure. And you have a mantle geotherm, how geotherm temperature pressure varies with the depth within the earth, you can see. And then you have different phase transitions. Diamond graphite intersection happens, we all know, at around 150 kilometers. Coesite, stishovite, very high pressure phases, polymers of silica, their transformation happens at depths corresponding to 250 kilometers. Then we know that the orthorhombic olivine, it polymers to phases like wachsleite, ringwoodite, they're all different polymers at different pressures. Even the garnet, very common mineral in the crust and upper mantle, with the depth it becomes majoratic type of garnet. We all know the silicon in normal garnet is in fourfold coordination, but in majorite it exists in fourfold as well as sixfold coordination. So what I mean to say is, as you go deeper into the earth's depths, the minerals also change their physical form, their crystallography will get changed. Clinopyroxene is stable, more stable than orthopyroxene, and you also get HPCPX, that is very high pressure clinopyroxene, which is stable. Now, how do we know these things? We know these things primarily based on experiments. And also whenever we find natural samples, we believe these things really happen. Next one. Now, one of the important natural proxy which tells us things which come from Earth's transition zone or even lower mantle is diamond. Diamonds, if you look at all the literature and compile, diamonds are sourced right from lower mantle through transition zone to upper mantle to upper part of sublithospheric mantle. So diamonds are sourced from all these areas, but your magmas always come from lithosphere or from these depth around 150 kilometers. So you can ask me how diamond has been transported up from that depth till there. We have a concept called mantle plumes. These mantle plumes are thermal disturbances which arise from the core mantle boundary, and while coming up, they pick up these diamonds and they are brought and transported into the source region of the magmas. Then you can ask me, how you know diamond is a carbon, it is coming from that depth? Because many of the diamonds, 90% of the diamonds carry inclusions, silicate inclusions. You can date the inclusion, or you can estimate pressure temperatures in those coexisting inclusions, then you can know the depth, your temperature, pressure, and age of the inclusion as well. So based on these things, the Stachel et al. In 2005 have shown the provenance of the diamonds comes from right from lower mantle up to here. Next. Now, before I go, I always feel we should also remember the great scientists whose works in the past have helped us to build up our models, like Norman Bowen, who is considered father of igneous petrology, the great experimental petrologist who made a lot of predictions, including differentiation and all these things, which are valid even today. Next one. And Ted Ringwood, on whose name the ringwoodite mineral has been named, he predicted in 1962 itself that high pressure polymer of silica exists in the lower mantle, but it was verified only 10-15 years ago. But the name ringwoodite was given to that in his honor. He is no more. But what he predicted in 1960s was proven just a decade ago, I will show you. So he's one person who was served as a professor at Australian National University at Canberra. Next one. And Joe Boyd, again, lot of the mineral phase equilibria at the deep mantle were all predicted by him. He combined very elegantly geochemistry and geophysics together. So he worked at Carnegie Institute of Washington. Next. And last, Peter Weil, he's still going strong. He's at Caltech. So he did a lot of experiments, especially on kimberlites, carbonatites, and these phase diagrams. And many of his models, including volatile fluxing, are still valid today. Next. Now coming to the title itself, Jules Verne, he wrote a very influential novel in 1864, Journey Towards the Center of the Earth. Of course, he wrote many other books like Around the World in 80 Days and so forth. So what he wrote in that book was, there exists a huge ocean in their center. That's a movie which came in Hollywood also. Next one. Now, a paper appeared in Nature a decade ago, exactly 2014, where scientists, a group of scientists have recorded within the diamond the mineral ringwoodite, which was predicted way back in 1960s by Ringwood. Now, what the importance of ringwoodite is, it contains up to 10 weight percentages of water. Of course, this water is what you call structural water. It is in the structure. So we call olivine, we all know, is an anhydrous mineral, but if it contains water, nominal water, it's what we call ringwoodite, and that ringwoodite is stable only at lower mantle transition zone depths. So these scientists, they have recovered a diamond with natural ringwoodite within it. So that actually changed the way of looking at the lower mantle. Next one. Now, because if you see, when plate tectonics began is $1 million question. People, there are different arguments. There is no doubt that there was plate tectonics since the end of Cambrian, but whether it operated in Hadean, whether it operated in the early Archean, so a lot of question marks are there. Of course, the present consensus says it operated, but the style of operation is entirely different compared to how the Phanerozoic it's operating. Next one. Now, coming with this background, we are coming to the eclogite itself. Now, eclogite is a bimineralic rock. Now, eclogite has a evolutionary cycle. So, eclogite can form as a cumulate. What is eclogite? If you analyze an eclogite, it's exactly similar to a basalt or a gabbro. Only the mineralogical transformation happens because it's a high pressure metamorphic phase. So, eclogite can be generated in different settings. For example, differentiation as cumulates or complementary melts, you can find that is in stage 1. You can see in mid-oceanic ridges. Then you can, seawater can interact with this magma which is coming up. Then it can also change to changes. Now, we all know mid-oceanic ridges supply fresh magma to the plates, and the plates gain density after they solidify and they subduct. And as they subduct to deeper depths, then they undergo eclogite phases metamorphism. They gain density, they dehydrate, and that eclogite may delaminate with increase in density, and if it melts further, it may give rise to a basalt. So eclogite, and it may be picked up by kimberlites and all to be brought up to the surface. So this is what is called an eclogite engine, and it depends on at what stage you are recovering the eclogite. So the point is, eclogite can be picked up by rock types like magmas like kimberlites and all, because they can come from those depths, and they provide a lot of information to us about things happening in the deep mantles. Next. Now, these eclogites have been recovered all over the world. So you can see wherever cratons are there, you find kimberlites. There is an association between cratons, that is the regions which have been stabilized since 2500 million years, which were not subjected to great orogenies. We call them cratons because on Earth's surface, no surface theoretically is stable. Even place like Hyderabad experience minor tremors. But the point is that Dharwar craton, Bundelkhand craton, after 2500 million years, never experienced a major orogeny. So we define those areas as cratons. So these, all the world known cratons, including the Antarctica, the eclogites have been recovered. Next one. And to answer the question, when plate tectonics has actually started, the answer came in 2011 that when people started studying the diamond inclusions, there are two types of diamond inclusions known in the nature. One is peridotitic and second is eclogitic. So I showed you eclogite is essentially formed, can essentially be formed by subduction of your oceanic plate. So eclogitic diamonds actually start appearing only after 3 gigayears. So all the diamonds which were found, others in peridotic diamonds, they were there before 3 gigayears. So scientists have suggested that plate tectonics perhaps started only from 3 gigayears because there is no incidence of eclogitic diamond before 3 gigayears. It's based on a huge sample set. There could be statistical anomaly also, but nevertheless, it still holds good. So based on these things, we believe that plate tectonics started at least 3 gigayears as shown by presence of eclogitic inclusions in diamonds. Next. Now, this is what the major events which happened in the Earth's history. You can see different supercontinents were formed and all that, but all the scientists who proposed plate tectonics has started, their names are given, the time scale with which they started were given. But the point I want to make is your Neo-Archean, Meso-Archean, what you call the oldest subduction related high pressure eclogite was derived at 2.1 gigayears. I am not talking about eclogitic inclusion, I am talking about the eclogite itself. That means towards the Neoarchean time, there are eclogites which have been recorded. That means definitely plate tectonics started around that time. Next one. Now I take you to the southern India, Dharwar Craton, where I spent a lot of my time initial years, and even now I continue my researches. So Dharwar Craton, you all know, is made up of two subcratons, what we call the western and eastern Dharwar. Nowadays, a new concept has come up. There is a transition craton, central Dharwar Craton also exists according to Jayananda and his group. But nevertheless, this yellow star refers to a place which is a very famous one in Indian geology, which is called Vajrakarur Kimberlite Field, where hundreds of kimberlites have been recorded by Geological Survey of India essentially over past 40-50 years. And this is where the Vajrakarur Kimberlite Field is, and towards the right is a geological map where a lot of kimberlite occurrences are shown. So I will take you to a place called Kalyandurg, where again a number of kimberlites occur, and many of these kimberlites are diamondiferous. Of course, they are not amenable to mining, but they are all diamondiferous. That means they are all derived from depths of 150 kilometers. Next one. So while during COVID time, as I told you, going back to the beginning, so Amitav Chatterjee joined with me as a postdoc. He came from Japan. He joined IIT Bombay. From there, he joined me. I asked him to work on another site from Chilka Lake complex, but due to COVID, he could not go to the field. Then he said what to do. Then I said, I have a lot of eclogite samples lying with me since 20 years, so you work on them. So while working on them, these are the samples we collected long back. He said one day, sir, I found some quartz in an eclogite. Can you change the slide? So you all know basalt cannot contain quartz, modal quartz. And basalt, chemical basalt, if you analyze it in CAPW norm, it may say, but modally, it cannot contain quartz. Likewise, eclogite, theoretically, it should not contain your quartz. So I said, what you are looking at could be an coesite. You know, coesite is a high pressure polymorph of silica. Now, this is a backscattered electron image and scanning electron microscopy. So this eclogite sample, we have found a mineral at that stage we suspected to be coesite, because EPMA or microscopy cannot tell it is coesite or not. You need to depend on XRD Raman to confirm it. But I am showing you, this is how a coesite was there. Of course, omphacite, kyanite were there because it's an eclogite. We also found an interesting phase. This is coesite. These are all different forms of coesite. The garnet which was there, some garnets were anisotropic in nature. A student of BSc also knows that a garnet is always isotropic under microscope. Then we realized there are some garnets called majorites, which I mentioned, which are weakly anisotropic. So we found two types of garnet, one strongly isotropic, other one are weakly anisotropic. Next one. And this is the coesite. That's how in PPL it looks like. That is in XPL. This is coesite. This is polycrystalline quartz associated with it. That is the omphacite. And this is the majorite garnet, which is anisotropic. I cannot rotate it, but it's an. So this what the assemblage we suspected. Next one. Then it was in a thin section scale. Now how to confirm? Because for XRD, powder XRD, you need to separate and make a powder. So then we were looking for an XRD in India where it can analyze your thin section scale, the different phases. Then we realized there are two places in India where such facility exists. One is at IUAC New Delhi, other is IISc. And IISc thing was down during COVID time. Then Amitava went to Delhi with some difficulty, and we could work on that IUAC XRD, where you can use your thin section and you can bombard your X-rays and you can get the spectra, which confirm all the red area bands you can see here are coesite. Of course, blue bands are quartz. So in our eclogite, we do have coesite, we do have quartz, because quartz is always associated with coesite, because coesite is a high pressure polymorph. As it is brought up, it is metastable, it inverts to quartz, but it's not necessary that entire coesite should invert to quartz. That's why we are finding few coesites intact and few quartz grains. That's polycrystalline quartz, what it means. Now to reconfirm it, we did Raman spectrometry. Raman spectroscopy is a very, very important technique, non-destructive technique. which shows Raman mapping, where we confirm that we do have a quartz and coesite association according to this Raman spectrometry. Now, coesite is a very important high pressure mineral. It is considered as an index mineral of ultra high pressure metamorphism. These two papers actually were very sensational, which came at the beginning of this century. Scientists from Wadia Institute of Himalayan Geology recorded coesite from an eclogite at a place called Somurari, which is a very famous place close to the Pangong Lake. So what this discovery tells us is, everyone knows that Indian plate is subducting below the Eurasian plate, but how far that plate is going, what is the concrete proof? The discovery of eclogite tells that this plate has subducted at least up to 100 kilometers where your coesite is stable. That's what, and it was brought up. So these two papers, discovery of coesite from Indus suture zone, actually made people to look at more seriously at ultra high pressure mineral assemblages. Next one. Of course, your coesites also can be formed by shock metamorphism. If a meteorite comes and hits the surface, then if you have sufficient amount of silica, then it can generate coesite as it was recorded in Lonar Lake. That is the other way you can generate your coesite. Next one. Now, you can distinguish chemically based on EPMA data, based on their silicon and magnesium cationic proportion between normal garnet and majorite. I mentioned the silica content occurs in high silica content in majorite. It beautifully brings out the silicon 3.05 is the cutoff. This is the normal garnet composition in my eclogite, and these are the your majoritic garnet composition. You can discriminate between them very easily. Next one. Now we also have done Raman spectrometry to spectroscopy to reconfirm whether we really have a majorite or not, which matches very well with the majorite data which is available in the literature. Next. Then we have calculated the pressure from which this majorite garnet was derived, because there are very good geobarometers which are available in literature. This is the data generated by us, and these are the pressures which were computed based on geobarometry. You can see they were all derived from a range of pressures 11.3, 17 gigapascals. So they are coming from extremely deep depths than we can think of. And we have also analyzed the CPX which is present in our sample, and that turned out to be a potassium-rich omphacite, and that potassium-rich omphacites are recorded from diamonds as inclusions. That's why it is shown as a mark. So that all these things point out to a very high pressure assemblage which is there in our sample, and you can use potassium in CPX, sodium in CPX, and you can again calculate the pressure from which the CPX is coming up. It again shows it is coming up with a range of pressures like 6 gigapascal to 10 gigapascal. Next. So what it all tells? It all tells we have a very high pressure assemblages, majorite, your K omphacite, and of course you have coesite. Now if you want to interpret it, this is what we have done. This is the majorite stability field. This is where 300 kilometers depth to 650. This is the field where majorite is stable. This is where your coesite is stable. And these are the PTs which are already available in the literature by Dongre et al. 2015. Here, that's what the PT of the Vajrakarur kimberlite field. And this is the PT which was given by Patel et al. On eclogites in 2009. But what we are telling, based on the data which we generated, our eclogite must have come from depths of lower mantle, because for the simple reason, the range of pressures which are calculated. So what we proposed was, perhaps in the Neoarchean time, in the Dharwar Craton, there was a deep subduction event, and during the subduction, the quartz in the crustal material got subducted. It formed the source for coesite, and to generate majorite, it must have gone to depths of at least majorite stability field, and because some majorites are showing very high pressure, maybe it has gone up to the lower mantle, and later on, due to some mantle plume, your sample has been brought up. You know, in science there are two things: what is fact, what is fiction, as Jules Verne did. The fact is you have a majorite, you have a coesite, you have a coomphacite. This is a model which we erected, that all these phases are formed perhaps due to very deep subduction, and while coming up, this coesite, some of the coesite because it is metastable, it inverted to quartz. That's why you are seeing in the thin section polycrystalline quartz associated with the coesite. So we published this paper a couple of years ago in Geological Magazine from Cambridge University, mantle transition zone derived eclosite xenolith in a diamondiferous mesoproterozoic kimberlite, because the kimberlite, the host kimberlite was dated at 1.1 gigayears. So obviously eclogite must be older. What we are now trying to do is to date the eclogite to know when it was formed. So we are on the process with it. Next one. So what I want to tell my colleagues, especially younger colleagues, when we studied earth sciences, I studied in 1991, we were taught that earth has a core, crust and mantle, which it still has, but the only difference is the earth is much more complex system than people envisaged in those times. If you integrate geochemistry and geophysics, earth is a interior of the earth. You have super plumes which are coming up. There are slabs which are going down, some of them going even up to deep mantle depth. So Earth's mantle, deep mantle, is a graveyard of slabs. A lot of phase transitions takes place. So modeling Earth, the deep Earth processes is extremely complex compared to modeling atmosphere or oceans, because the variables are many. So you need to keep in mind whenever we try to come up with models. So Earth's mantle is extremely complex, and you have reducing conditions, oxidizing conditions. You need to consider all of them. So this is my last slide. So as Dr. Dora, I was very impressed when he said, mineralogy is the mother of all petrological sciences. I tell my students, many of them are sitting here. It's very nice to catch up with them. I told them in their very first class, if you are good in mineralogy, you are good in petrology. If you are good in petrology, you will be a good in earth scientist. That's what I believed in. So mineralogy plays a very crucial role in understanding earth system science. All the elements you analyze in your rocks, they have to be present in some mineral. So if you know what the mineral is, then your answer will be easy to address anything. Either you do isotopes, you do critical mineral study or whatever. It should be a mineral-based approach. And 3 M's are indispensable, as somebody told me long back in my career, in tackling any scientific endeavor. One is the material. You need to have right material. You need to have right instrument. And you need to have inquisitive, interesting mind. Then you can do good science, and perhaps you will enjoy it, which every scientist does. And I come from this institute, National Center for Earth Science Studies, which is a 46 years old institute started by a Director General of GSI who retired from GSI, and he started that institute, Dr. Karunakaran, who also discovered the Mangampet barites, world's largest producer of barites. It's in Kadapa Basin. He was the man who discovered it. So this institute was taken over by central government a decade ago in 2014. It comes under Ministry of Earth Science, and it's a very young institute in terms of manpower. The average age of scientists is only 40. I am the oldest one, and a couple of other people. And we have all the best facilities, including we can date minerals, accessory minerals. We developed the protocols to date apatite, titanite, one of the first labs to develop in India. And we have, you people can visit our website, and anybody is interested to collaborate, you're all more than welcome. And it is located in very beautiful city of Thiruvananthapuram, and a pollution-free city. And it's really God's own country, because I experienced after going there. I've been to many places, but this is a place, I never seen such a place in India or even in abroad. Very beautiful place to live in. So you are welcome to visit on personal or even professional way, and a lot of opportunities exist for collaborations. And I should acknowledge very deeply, SCRB today, nowadays it's called ANRF, it supported my research throughout, and my research scholars and students, without them, the story would be entirely incomplete. Thank you very much. So, yeah, please. Obviously, the subducting plate must be an oceanic plate. Okay. Yeah. So now, if you look at how Dharwar Craton has evolved, there are two subduction theories. One is subduction from the west plate has subducted, or subduction from the east. There are two models which are in vogue. Now the crust is all it doesn't matter whether it's oceanic or continental. Continental crust cannot subduct to that depths as far as we know. But oceanic crust can subduct, it can create your cratonic material like granites. So we did not touch that point. What we touched is that plate which got subducted was certainly your oceanic plate, because its density is high and it is capable of giving your eclogite. Eclogite is nothing but a oceanic crust metamorphosed. So the plate which is subducted is oceanic, and very likely the plate which was there could be another oceanic, we don't have any clue, or it could be continental also. That aspect, we have no control on that. Okay.
So actually the question is in continuation. When you are referring that the diamond of peridotic diamond and eclogetic diamond, and based on that people are trying to differentiate the plate tectonic started or not. So that crustal thickness over this time frame was different. So if the crustal thickness played a major role in the high pressure metamorphism when subduction was going on, so could it be a factor the crustal thickness could have controlled it in another way?
We know very little about the thickness of the crust at that time. Crust has grown over geological time. That's the first thing. Second, we don't look at in mantle as a crust. We look at lithospheric scale. That means crust plus upper mantle combined. Then that is a conductive lid that could have exercised, but we don't have any control. But what eclogetic diamond is, the same mineralogy which you find eclogite, you are finding there. Peridotic means your olivine plus OPX plus CPX is finding. So this is the terminology they used. Okay, and it's a samples based in all the cratons. It's a statistical thing. Not a single eclogetic diamond bearing inclusion diamond was ever recovered till today. So based on this, they have inferred. Okay, now you need to consider erosion also. So many things we don't know. What we see is something different. It could be. It could be there. It could be very different at that time. Okay.
Thank you, sir.
Yes.
So in this majorate sample, did you find like any studies has been done that can indicate, apart from it's also magnesium silicate, a majorate composition. So is there any other element substitution which has also been found from the studies?
Yeah. A majorate is a garnet solid
Yes,
solution,
yes.
not olivine.
But yeah, it's not. I told olivine as an example.
Yeah. No, chemically you need to calculate the formula.
Yes.
Then it will assay very differently. Your silicon will be very high.
Yes.
That's the index of majorite.
Okay.
Okay, the silicon is the difference. Otherwise, your MgFe, they are all similar. Your stoichiometry silicon will be excess than what you expect in a normal garnet because of your six-fold coordination. That's the only thing.
So
And also, it's anisotropic in nature.
yes.
Yeah.
So like suppose how will like I do like high pressure mineral physics, mostly experimental mineral physics. So here we take only one mineral and put pressure in it. Suppose, but Earth system is not like that. We have so many minerals like olivine, orthoperic. So like how that stimulation has not yet been done. It's quite difficult to do in diamond anvil cell. So how people do high deformation experiments. So like such kind of studies can be done like
No, people are doing.
people are doing, yes. They are doing like high pressure, but suppose there are so many variables in it, like water, that you tell structural water. So that is there, volatiles is there. So all this like the mantle geochemistry. So how can we put it in a model form, like integrate everything together?
You look at all your phase diagrams.
Yes.
They are binary, ternary, quaternary.
yes.
So your variables, you are fixing them.
Yes.
The entire game is
Yes.
between them only.
Yes.
It cannot be invariant. Okay,
Yeah.
so you need to know why we are doing what is the objective and
Yes.
play around with that.
Yes.
But it has no value unless you find natural sample.
Yes.
It can be there theoretically.
Yes, yes.
Like Bowens gave that differentiation theory. If it is not validated in the field, it has no meaning.
Yes.
So that's why ringwoodite has gained importance after discovery of the mineral.
Yes.
Got it?
Yes.
Yeah.
Yes.
Yeah.
How many number of samples you found the
Yeah.
the cohesite that
Yeah.
mineral, how many samples have you found it in?
Yeah, first thing is age of the kimberlite was dated very well. 2, 3 different techniques by, it's already published by people from NGRA, people from us, perovskite, phlogopite. It is 1.1 gigayears, that kimberlite. We published in Chemical Geology, this thing. Now, how many sample? We collected samples from there. Only in one thin section we have found. I mean, there could be many, but this we sampled from the Kalyan Durg, that pipe exposure. So only in one sample, in one thin section I could find. In others we tried, we did not. So that's not our fault, it's a nature's fault. So what
Thank
can
you,
we
sir.
do? Yeah. No, the thing is, in geology we look for anomalies. We don't want the same thing. So all geologists, geophysicists look for anomaly where there is a difference. So we, to answer you, we could find only in one thin section which we preserved. Okay? Yeah.
Hello.
Anybody?
Hello.
Huh? The omphacite. Omphacite itself is a high pressure CPX and which is also potassium bearing. Normally CPX doesn't have potassium. So to incorporate that potassium, it has to be at that deeper pressure. That's why I showed diamond inclusions only you get potassium rich amphasite. Yeah, but the point is, we should more sampling. If GSA gives more samples, we can work on more, and we picked up from the field actually. Yeah, more samples better, we may find many more phases. What I want to emphasize is how important instrumentation techniques nowadays. That's what I want to drive. You need to use them, and now GSA is very well equipped with so many labs which were not there when we started our careers. I think we need to make use of these techniques so that we can find things which previously people worked. We should not say that he worked there, why you should work. I mean, nothing in print is Bible. Everything is open. You can rewrite what people have done in the past. Because today we have instrumentation. CT scan is there today. 30 years back it was not there. So you need to be you should be savvy of the technology. Na? Cricket also we use third umpire, which was not used before. Decisions will be correct.
Okay, thank you, sir, for an engrossing presentation. Whether it's a novel or a Hollywood movie or a lecture by SAD, it's always engrossing. Thank you, sir. Thank you very much. Yeah.
Thank you. I forgotten that I am the chairman, so I might have taken some time. So I think our next speaker is Arya Ghosh, Vikash Tripathi, Balakrishnan. They would be, I think, who is going to present? Arya Ghosh? Yeah. She would be presenting on integrating field and microstructural techniques for kinematic analysis of porphyroclast shear zone, Achankovil shear zone, southern India, close to the place where I live. Okay?
Very good afternoon to everyone. So I'm going to discuss about some very basic techniques that we have applied in our study by integrating simple field and microscopic study in a shear zone where there is no porphyroclast. So this is the story of a shear porphyroclast deficit shear zone. And in this case also, how we can estimate the kinematic vorticity number and how we can determine the entire kinematic analysis in this shear zone. That is the main focus of this study. So why we preferred the porphyroclasts in a shear zone, I'll just tell in brief, because the porphyroclasts have got very distinct shape. They have got well-established geometric structures like delta type, phi type, sigma type, and many others that indicate the shear sense. And also they have got an aspect ratio that can be easily measured, the rotation angle that can be easily measured, and those can be applied in different techniques. Like here I have explained I have given example of two techniques, which is porphyroclast aspect ratio method and the porphyroclast hyperbolic distribution methods. There are many more. So the porphyroclasts are basically very much preferred for any kind of kinematic analysis, especially where the vorticity number analysis is involved. So in case of a shear zone where there is no porphyroclast, we have to look for some other methods, some other like relatively non-conventional methods. So one of these is use of the oblique foliation. So the locating the oblique foliation in the microstructures itself is a bit tricky, but of course if we be careful to choose the proper sections, we can get this oblique foliation, and this oblique foliation can be used as a very good vorticity gauge. So this is just a quick look at the theory. So the oblique foliation is nothing but the instantaneous stretch axis, which is this one, and the angle between the myelonetic plane and the instantaneous stretch axis. If we can measure this one, we can use this formula to get the kinematic vorticity number. It's not difficult. The formula is very simple, but to get the oblique foliation is a bit tricky. Now we will see how we can choose the proper section where we can have that oblique foliation. So for any kind of kinematic analysis, we have to look at the vorticity profile plane. So what is a vorticity profile plane? It is the plane, like here, the blue colored one. The vorticity profile plane is the plane which is perpendicular to the vorticity vector. And vorticity vector is nothing but the axis of rotation of the rotational component in any shear zone. Now we cannot see this axis in the field. So in the field, how do we determine which one is the vorticity profile plane? So in the field, we rely on the field features, the asymmetric features. The asymmetric features will be maximum on the vorticity profile plane. And if we do not have that also, we can construct the vorticity profile plane. The vorticity profile plane will be necessarily parallel to the shear direction. Please note that this is shear direction, not the x direction or the stretching lineation direction. It will be parallel to the shear direction and perpendicular to the myelonetic foliation. So this diagram shows as the shear direction changes, the orientation of the vorticity profile plane will keep on changing. So we have to fix the shear direction first to get the correct vorticity profile plane. So once we fix it, the shear direction and the normal to the foliation plane, these 2 points, we can construct the vorticity profile plane very easily. Now coming to the study area. So the study area is Achankoville shear zone. It's a very well established shear zone which has northwesterly strike and southwesterly dip. It is mostly a sinistral sense shear zone. Most of the stretching lineations that are available in these shear zones are subhorizontal, and the asymmetric structures that appear are also on the plan view or the planes which are very close to the horizontal plane, on those planes only. So if these are some of the field photographs and some of the photomicrographs which says that what is the shear direction in Achankoville shear zone. So as I said, there are not much porphyroclast, only 1 or 2. So from that asymmetric tail, from some shear bands, from SC fabric, we can see that a sinistral sense is very prominent. And this sinistral sense also corroborates when we do microscopic studies. The new sin shearing mineral that grows, it follows, I'm so sorry, the pointer is not visible. Okay, so the new sin shearing mineral that grows, that follow the existing sinistral sense of the shear, and this way we can also say which is the shear direction. So this is the CC dash fabric. So broadly, it represents a sinistral sense. Now, if we come to the stretching lineation, in most of the cases, the stretching lineation is subhorizontal or very shallow plunging towards southeast. So this is the orientation of the stretching lineation. We can say that these are subhorizontal. So there we have taken a mean orientation, the geometric mean of the orientations. So the vector mean, vector mean. So it shows a very shallow plunge towards southeast. Now, to construct the vorticity profile plane, as we took help of the diagram in the beginning, so this is the Achankoville shear zone. We considered this one. So northwesterly striking and southwesterly dipping myelonetic plane. This one is this pink plane. This is the myelonetic plane. Now, we have to fix the shear direction first, as I said. And from the plan view, we have seen that the shear sense is sinistral. That means the shear sense can be seen on the plan view, means it's a strike slip kind of a shear sense. So it will be horizontal plane, and the stretching lineation is southeasterly plunging. So we can say that since the stretching lineation and the plane where we see the maximum asymmetric structures are subparallel, we can say that the stretching lineation here represents the shear direction as well. So we can take this plane, the plane that passes through the stretching lineation, and the perpendicular to the myelonitic foliation as the vorticity profile plane. So this is the classical lineation parallel foliation normal plane, which also is the XZ plane. And apart from that, we have seen that in the field, the plane which is parallel to the strike of the myelonitic foliation, but it is actually the plane which is having strike parallel to the myelonitic foliation, but it is actually perpendicular to the myelonitic foliation, this blue colored plane. We call it foliation parallel or SPL plane. These planes also preserve very good asymmetric structures. Now why? Because this is very close to the vorticity profile plane. So these two planes are subparallel and they preserve very good asymmetric structures. So both the planes can be used for the shear sense studies, but we always prefer the vorticity profile plane. So now once the plane is fixed, what we did is we have done oriented section study. So in the field itself, we have fixed the vorticity profile plane from the orientation of the lineation and the foliation, and then we cut those sections which are parallel to that. And then we had a closer look into those sections, and we could figure out the oblique foliations there. So this is represented by the recrystallized quartz cluster. If we trace the individual grains, it looks like this. So we can see that the long axis of these grains form an angle with the C plane. Now we are doing this study on the plane of the microscope stage. But the vorticity profile plane, as I said, it is a dipping plane, as I showed in the earlier block diagram also, but we are doing it on the microscope stage, so it's a horizontal plane. So what we have to do to make this angular measurements correct, we have to rotate this plane, vorticity profile plane to horizontal plane. So this plane was rotated, and it was made like that. Now this peripheral horizontal plane of this stereogram, this represents the vorticity profile plane. And we have plotted the angle between the C plane and the long axis of each and individual grain here. Like all the points are represent the long axis orientation of the individual grain that are present in the oblique foliation. So once we do this, we get the vector mean of it, which is this, and we get the final angle between the two, which represents the angle between the instantaneous stretch axis and the C plane. So when we use this formula, after Wejerma's 1991, we get the kinematic vorticity number, which is in this case, it is 0.997, very close to 1. Now the similar kind of study we did in another section to check the repetitiveness of our estimation of kinematic vorticity number, and we get a similar number. It is 0.990 in this case. So from this, because the kinematic vorticity number is close to 1, we can say that it's a case of simple shear. So to conclude, from this simple exercise, integrating field and microstructural techniques, we have got that Achangoville shear zone is a shear zone that represents a simple shear. And also, because there is no variation in the asymmetric structures on the other planes except the VPP or the foliation parallel sections, the SPL sections that I told. So all are in the same orientation, almost subparallel orientation. We can say that this is a monoclinic symmetry shear zone. So these simple studies can lead to the major conclusions that we sometimes take after a very long series of studies, including very complicated techniques. So that's it, I think. Thank you so much, sir.
One or two questions, anybody? Did you use U-stage?
No, sir. Sir, this we use only, U-stage or the EBSD techniques, sir. Those are for the crystallographic preferred orientation. But here we tried to focus that if we do not have that option, we can do it the same thing by shape preferred orientation. We just have to figure out the correct plane and the correct grains
Yeah,
which
but
to
you
measure.
always have the option of confirming it from EBSD.
Yes, sir,
At
yes, sir.
Kharagpur IIT, Professor Mamtani is here in his lab, he has got. Okay?
Yes, sir, yes, sir. Sir, actually, we discussed this and we tried, but somehow it couldn't be materialized. So, of course, we will do it in future and we'll cross-check this, sir.
Acha, about Achan Kovil shear zone,
Yes,
what
sir.
is the interpretation? People like Jay Gopal Ghosh and all did lot of work in that domain. Does your study confirms with their argument or it is different?
Sir, regarding the terrain boundary or not, you are telling, sir?
Yeah.
Sir, actually, our study was not for that specifically, but still, sir, we have done some that UHT metamorphism study also we did. What we found that this shearing is also a UHT shearing, which is not recorded in many of the cases. As I showed, sir, the syn shearing mineral growths. So we can see the garnet is broken down to orthopyroxene. The garnet which are asymmetric in nature and the orthopyroxene which are formed after the garnet, those also follow that asymmetry. And if we do a temperature estimation from the orthopyroxene garnet, it is UHT. And that UHT metamorphism is of Pan-African age. Now, Pan-African is the major time where the orogenic thing happened. So, sir, it may represent that major kind of a terrain boundary, but for this, as of this study is considered, sir, we didn't study it in that point, sir.
No, I got it. No, I
Yeah.
just asked the geological context of your finding.
Yeah.
You mentioned at the end,
Yeah.
you commented on the
Yes,
Achan
sir.
Kovil, this thing. That context I wanted to know. That's it.
Yeah, sir, actually, sir, we have many of the shear zones in India where we have done many things, but the kinematic analysis is missing in many of the cases, the systematic kinematic
Like
analysis.
Kaveri shear zone, people
Yes,
have
sir.
interpreted as a flower type of structure,
Yes.
which is beyond your monoclinic symmetry.
Yes,
That's
sir.
why in that context I asked,
Yeah,
what's
yeah.
the view of people before you?
Yes, sir. Yes, sir. Sir, it is definitely not like that,
Okay.
sir. Yeah. Yes,
Anybody else or we'll go to the... Yeah, yeah.
Sir. Yes, sir. Sir, this shear zone, because it's a very high temperature shear zones, so most of the minerals that we get are formed within a particular temperature bracket, I guess, sir. So this, at this temperature, the mineralization will not be stabilized possibly. So it is not a good area, that's why we don't have major mineralization here. But there are some mica occurrences, like the Punalur mica mine, which is a famous mica mine. It is solely of a phlogopite mica mine. So you can understand, because it's a very high temperature metamorphism, so the mica form that we get there is only phlogopite. And apart from that, sir, recently we have got some pegmatitic bodies which contain high niobium values. We are looking into that. So those kind of like, yeah. Yeah, not related to the shearing. It's a post one, yes. It cut across the myelonitic fabric, yes, sir.
Thank you.
Thank you, sir. Yeah, thank you, sir.
Just a quick, very impressive that you are trying an innovative approach in your work. If we don't have a asymmetric class, if we can't find, still can we apply this technique?
Yes, of course. Yes, of course. But it is, I'm telling, oblique foliation, we generally do not get easily, because whatever crystallization you get, those are due to progressive shear, they become parallel to the plane C plane. This is something where the instantaneous stretch axis got freezed. So you have to get that one. So you have to be very careful while choosing the plane, because if you don't choose that plane, you can never get it. But if you choose that plane, you may or may not get it. So it's like that. Yeah.
So the next speaker, thank you very much. And the next speaker is, I think, Arindam Das. He would be taking us to Gadwal, Himalaya. Yeah. He has got 12 minutes. They say that there is a valedictory we need to complete by 6:30, but
Hello, hello. Hello. Yeah. A very good evening to all. So today I will be presenting on dynamic recrystallization mechanisms and estimation of strain rates across main central thrust zone, Alaknanda Dholikanga valleys in Garhwal, Himalaya. So this work was done under the supervision of Professor Shantanu Bose, Presidency University in Kolkata. Next. Yeah, so quickly I will discuss about the generalized geological map of the Himalayan orogen. So if we go from south to north, we come across several crustal scale faults within the Himalayan orogen. So if we start from the south, first comes the main frontal thrust, which has brought along the Shivaliks with the Indo-Gangetic alluvial plain. And then further north comes the main boundary thrust, which has brought the Proterozoic lesser Himalayan sequence with the Shivaliks. Further north comes the main central thrust, which has brought the high-grade metamorphics of higher Himalayan sequence with the Proterozoic lesser Himalayan sequence. And further north come the STDS. This is the South Tibetan Detachment System, which is believed to be a zone of extensional faults, which separates the Tethyan Himalayas from the high-grade higher Himalayan sequence. And further north, eventually we come across the Indo-Sanpo suture zone, and then we go on to the Eurasian plate. So just a minute, the earlier one. So this is the area of our interest, the present study area. Next. So this is the geological map of the study area. So basically we have the Joshimath formation and the Suraithota formation, the upper two formations, which comprise a part of higher Himalayan crystalline that is thrusted over the lesser Himalayan sequence along the main central thrust zone. Now within the main central thrust zone, we see several evidences of shear localization, such as SC fabrics, radial shears, stretching lineation, and so on and on. The overall trend of the MCT here is northwest-southeast and with consistent dips towards northeast, as is evident with the stereo plot of poles for myelonetic foliation. We have collected samples right across the MCT zone to study the quartz microstructures to estimate the strain rates and to see the fractal dimension, how they differ across the MCT zone. Next. So as I have already mentioned that there are evidences of shear localization within the MCT zone. We see evidences of SC fabrics, radial shears, stretching lineation, occurrences of granite myelonite within the MCT zone. And all these, they show top to south shear sense. Next. Okay, so before discussing about the quartz microstructures, what we did was that we calculated the diameter of the or the grain size of the recrystallized quartz grains. Now what we did was that we very meticulously we calculated the perimeter and area of the recrystallized quartz grain in ImageJ software, and then what we did was we found out the area of an equivalent circle with an equivalent diameter as that of the recrystallized quartz grain. Now that diameter gives us the recrystallized grain size. Next. So yeah, as I have already mentioned, we have collected samples right across the MCT zone. So the first sample was collected 40 meters from the base of MCT. So what we observe here is the average grain size is 41.5 micron. Now here we can see these are the typical core mantle structures. These are typical of subgrain rotation deformation. Now if you can look closely, there are few evidences of new recrystallized grains being formed by bulging recrystallization. So here what we have observed, dominantly it is subgrain rotation with occasional occurrences of bulging recrystallization, and also the experiments by Steep et al. In 2006 and 2010, later in 2010, they have shown that the bulging recrystallization to subgrain rotation transition lies at around 40 micron for quartz. And then the next sample was collected from 930 meter from the base of the MCT. Here what we see, there has been a sudden marked change in increase in the average grain size. It has jumped up to 100 micron. We see wide scale development of ribbons, development of pinning structures, window structures, evidences of grain boundary migration. That means we have shifted from subgrain rotation to grain boundary migration within 1 kilometer distance. Next. Yeah, further going across, the next sample at 1.5 kilometer, the grain size has increased to 105 micron, and at 1.75 it has further increased to 108 micron. We see evidences of window structures here, so beautiful window structures in quartz, evidences of grain boundary migration. Next. Yeah, at 2 kilometer distance, the average grain size is 107, and again at 3 kilometer distance from MCT zone, base of the MCT zone, near the contact with the higher high-grade metamorphics of higher Himalayan crystalline, we see there is again another jump at 118 micron. We see wide-scale development of grain boundary migration. Next. Okay, to summarize, we started off at 40 meter at the right at the base of the MCT. There we observed that we have wide-scale development of subgrain rotation with occasional bulging recrystallization, and then progressively we see that grain boundary migration has taken a dominance. So basically, we started off at 141.5 micron and we jumped up to 108 micron farthest away from the base of the MCT. Next. Yeah. So with the calculations that we did for diameter of the grains of the grain size of the recrystallized quartz grains and the perimeter, so when we plot it in a log-log graph, they all fall in a straight line. So basically, this is nothing. The slope gives us the area perimeter fractal dimension. Now, this Takahashi et al. This we have taken from Takahashi et al. 1998, but Takahashi et al. Also borrowed it from Mandelbrot, who had given this equation quite 50 years back when he used it to predict the shapes of the irregular shapes of the clouds. So basically, we see that the in the y-axis is the perimeter, x-axis is the quartz grain size. We see all are falling in the straight line. So and with high R squared, that means that it's giving a very, it's showing a self-similarity or showing a fractal behavior. So what we have observed is that right at the base, the area perimeter fractal dimension is highest, and as we go away, the area perimeter fractal dimension falls, which is evident from the increase in grain size. Next. Yeah. Then we have calculated the differential flow stress. This equation we have taken from Steep and Tullis, 2003. They have arrived at this equation through experimental studies in Greek apparatus. So sigma equal to B into d to the power minus p, where sigma is the differential flow stress, d is the grain size, b and p are experimentally derived empirical constants. So what we observed was that the differential stress is highest at the base of the MCT. It is 37 megapascal, and it falls up to 16 megapascal furthest away from the base of the MCT. Next. Yeah. Now we have plotted the differential stress and the grain size in deformation creep mechanism map. Now this deformation creep mechanism map was constructed by Platt and Baird 2011, and this is valid for around 400 degrees centigrade and above. So the dominant mechanism fills diffusion creep, DRX creep, and climb assisted dislocation creep, and we have the strain contours here. These are the strain contours 10 to the power minus 10, 10 to the power minus 12, and these are in per second. Now what we observe is that all the samples are plotting climb assisted dislocation creep. That means they are giving evidences of high temperature deformation. So and all the samples they plot at strain rates around 10 to the power minus 13 to 10 to the power minus 14. Now these are quite consistent with the naturally occurring shear zones and the studies carried out elsewhere in the world. Next. Okay, so we have also calculated the strain rates using various quartz flow laws equations, which have been derived by various type of experiments. Basically, we have used two kind of perimeters. One is area perimeter. Two kinds of parameters. One is area perimeter fractal base dimension flow law, which has been given by Takahashi et al. 1998. And the next we have used is flow law, which is using differential stress. Now differential stress, we have used two kind of equations. One is Hart et al. 2001. This is a very famous equation. And next, and this is a very recent equation. It has been published in EPSL. Basically, Ghosh, who is a junior of mine, has worked on the Hart's equation, and basically these are all showing non-Newtonian flow. So basically, he has just changed the component in. The earlier it was 4 in Hart, and he has changed it to 2. Next. So when we compare the strain rates estimated from different flow laws, what we find is that the strain rate based on the area perimeter fractal dimension is giving 10 to the power minus 8 to 10 to the power minus 7, whereas those using the flow laws, using the differential stress gives us 10 to the power minus 16 to 10 to the power minus 14. Now, what we infer is that the flow laws which have been developed by Hart et al. And Ghosh et al., they are giving us the strain rates during this study, which is at par with the natural examples. And further, the Takahashi et al., the area perimeter based parameter, flow law gives us faster rates. Now, this what we infer is that because of the higher temperature which is within the MCT zone, therefore perhaps that's why the fractal based flow log is not giving us consistent results. Now similar thing had been shown in one of the paper by Mamtani sir in 2010, where also he had shown that possibly because of higher temperature, the fractal dimension based quartz flow law, possibly it fizzles out. Next. So to conclude, we see that the area perimeter based fractal dimension, it decreases away from the base of the MCT, which corroborates with the increase in quartz grain size and an increase in temperature. Further, we started off with subgrain rotation with occasional bulging recrystallization at the base, and now we get dominantly GBM as we go away from the MCT base of the MCT. Now the strain rates by flow laws using differential stress are giving us the results which are at par with naturally occurring shear zones. And further, the grain size reduction and the lower temperature at the base of the MCT, we feel that what we conclude is that this is because of the juxtaposition of the deeper level high temperature rocks which has come with the colder lesser Himalayan sequence, and therefore at the base we get higher stresses and lower temperature, and we go as we progress away we see higher temperature and gradual coarsening in grain size. That's it. Thank you.
Any quick question? If not, how does your strain estimates compare with that of GPS strain estimates in MCT?
Yeah, this is giving quite consistent, because during Gorkha earthquake, the recorded strain rate was around 10 to the power minus 14, minus 15. That's why we were saying that the quartz flow laws, differential stress based quartz flow laws are giving us very natural strain rates, because these quartz flow laws have been brought out because of these experiments in Griggs apparatus. They have done these experiments at faster strain rate, say around 10 to the power minus 6 to 10 to the power minus 7. But the thing is that the cross microstructure we are getting in that experiment is quite at par with the natural. So basically that's a scaling down thing. So it's quite consistent,
Thank you, Arindam. Please, ma'am, very quickly.
You have collected samples from MCT within a 1 kilometer zone. I want to know what is the nature of sample. Is it same in all the
These
cases?
are all deformed quartzites. Actually, all myelonetic quartzites. That's why we could do this kind of study.
Okay,
Because
thank
this
you.
is applicable only for quartz.
Okay, thank
We
you.
have flow laws for olivine also, but here we have worked on quartz. Yeah.
So I think we should thank the two speakers in this session
Thank
for
you very
coming
much,
up with very innovative models, and I'm sure these models also incorporate a lot of petrographic observations, field-based studies, and I think I encourage them to publish them in good journals so that they can be tested for their effectiveness much more. So with this, I thank the organizers for giving this opportunity to chair, and I should thank my co-chair also for extending his help. Thank you very much.
Sir, a big thanks to our session chair, co-chair, and all our speakers for their valuable contribution towards this session. So may I now invite Shri Shantanu Bhattacharya sir, Deputy Director General GSI, to kindly felicitate our session chair, Dr. N.V. Chalapati Rao, and our co-chair, Shri Avik Manna, with mementos as a gesture of our sincere appreciation for their guidance and support in this session. So with this, our last technical session concludes, and we will begin with the closing ceremony at 6:30 p.m. followed by dinner. I will request you all to please proceed for the closing ceremony. Thank you.